Hello everyone, my name is Joseph Stafurek, and today I will be presenting the research paper Hallucination is Inevitable, an Innate Limitation of Large Language Models, presented by several researchers from the National University of Singapore. So we've all seen examples when using generative AI models such as ChatGPT, where we get a confident answer from the model that is just simply wrong. Oftentimes we may assume that is simply an engineering issue that can be fixed with further improvements of the models. In other words, if we just get better data, bigger models, or smarter prompts, maybe these hallucinations will eventually disappear. This paper takes the opposite angle. It asks a foundational question about all large language models viewed as computational systems. It asks, if we use LLMs as a general purpose problem solvers, is it even possible to train one that will never hallucinate? The authors answer this using tools from computability and learning theory, and they argue that hallucination is not just a bug in today's model, but a built-in limitation of any computable LLM. In this talk, I'll first walk through how they formally model LLMs and hallucination, then outline their impossibility result, discuss what this means for real-world systems and mitigation strategies, and finally a personal evaluation of the overall strengths and areas for improvement of the paper. Before we begin, I would like to note that much of the information contained in this presentation should be accredited to the authors of this paper, including but not limited to definitions, theorems, graphics, and tables. So let us begin by briefly summarizing what this paper sets out to do. We all know large language models are incredibly useful, but they do sometimes produce confident, fluent answers that are simply wrong. This is what we call hallucinations. There does already exist extensive work in this area of interest, most of which try to reduce these errors. They do this with benchmarks, which include evaluations of how much a given model hallucinates. This way we can compare two models together and see which one is better, defined by a lack of hallucinations. There is retrieval strategies, which includes, say, you are working on some proprietary knowledge which a model may not be trained on. You can provide that model before it produces an output with that data, so that way it has access to the proper information to reduce hallucinations. Or some strategies include prompting, which is trying to break down entire tasks step by step to make a model reason through evaluation. But none of these actually tell us whether we can ever get rid of hallucinations completely. This paper tackles that question in a simplified mathematical setting. The authors treat a trained LLM as a black box function that maps text to text, and they imagine some ideal ground truth function, which we will define later, that always gives the, for this case, correct answer. We consider a hallucination as any output that does not match that correct answer. The key message from the abstract and introduction of this paper is that even in this clean, ideal world, no computable LLM can be perfectly correct on every input. So hallucinations aren't just a quirk of today's systems, but rather that they are a fundamental limitation that we have to design around. Before we can consider and evaluate the author's arguments for the inevitability of hallucination in LLMs, we must establish the context for within which they make this argument, including three important definitions. The author's definitions for large language model, a formal world in hallucination, and finally training an LLM. So first, let us establish how the paper formalizes a large language model, because this is foundational for all the theorems that we will discuss next. So in practice, we think of an LLM as predicting the next token given all previous tokens in a prompt. When fed a sequence of tokens, the model predicts the next token by token to produce a final complete output. The authors strip this down to a very clean mathematical view. They fix some alphabet of tokens and let S be the set of all finite strings over that alphabet. Then, once the model is trained and a decoding strategy is chosen, you can treat the whole system as a function H on input S, output S. The input string S is your prompt, and it returns an output string, the model's complete answer. This abstraction deliberately ignores all the internal architecture and probabilities and the optimizer. All the details are hidden inside the function H, and this lets us ask the very general question, like, given any such computable function H, can it ever perfectly match the ground truth function on all inputs? We will define the ground truth function next. But for this, the key takeaway is that for the rest of the paper, a large language model is just a total computable function from strings to strings. The power and limitations of LLMs are analyzed at that level, not at the level of specific neural network designs. It is also important to note that for each LLM, they have different states, which represent the stage of training that is in. A stage of training is mapped to the amount of samples that the model is being trained on. So now that we've modeled an LLM as a function of strings to strings, the next step is to define a clean world where we can talk about correctness and where we can define hallucination. So the authors offer an ideal ground truth function f, where for every possible input string s, f of s is the one correct output. The set of all pairs s and f of s is the formal world that we care about, and our training data is just a subset of these pairs. Our LLM is trying to approximate f based on these training examples. So in this setup, a hallucination is simply an instance of where on some input, the LLM does not match the ground truth function. Or should I say the output of the LLM does not match the ground truth function, or the output of it. Mathematically, this is when on some string s, h of s does not equal f of s. This is a very stripped down world, and it lets them ask a precise question. Can there exist a training procedure that makes h match f for every input? Or must there always be some hallucinations left over? That's what the rest of this paper answers. So for a final definition for context, the authors formalize what it means to train an LLM in their setting. So given our definitions of a ground truth function f and hallucination, they pose a single fundamental question. Is there any fixed training procedure such that for every possible ground truth function f, the procedure eventually reaches some trained state hi that matches f on all inputs? On this slide, we see a diagram that outlines our formal setup and shows how training actually works in this paper's framework. So the diagram has four main parts. First, on the left, we have the real-world corpus, the messy text data we typically train on. Conceptually, this is where our examples come from. So next, that connects to the formal world, where we imagine an ideal ground truth function f. From f, we can generate training samples, pairs of s and f of s, that represent perfectly labeled data for our task. Those samples then feed into the iterative training procedure in the middle left. As it sees more examples, it iteratively updates the model through states h0, h1, all the way to hn. Finally, on the right, the state hn is deployed as the final LLM, and it now takes unseen inputs s from the world and outputs hn of s, and this is exactly where hallucinations can still occur. So, at this point, we've established the scope and essence of the formal world established for this paper. We modeled an LLM as a computable function of strings to strings. We've introduced an ideal ground truth function f, and we've described training as a procedure that walks through states of h. Now, we will start the core argument of the paper, the formal proof that hallucination is inevitable. So the first key result looks at any computably enumerable class of LLMs. This just means, imagine you write down all LLMs that can ever be implemented on a computer. If you can, in principle, list them one by one with a program, they're in this class. The theorem says, for any such list of LLMs, there exists a computable ground truth function f, such that every single model on the list is wrong on at least one input. This paper essentially uses the diagonalization argument from learning theory as the primary tool to prove this. They do this by constructing an f that disagrees with model 0 on input 0, model 1 on input 1, model 2 on input 2, and so on and so forth. By construction, no model on the list can match f everywhere. We'll break this argument down into three main points. First, computably enumerable LLMs will hallucinate on some inputs. Then, LLMs will hallucinate on infinitely many questions. Finally, hallucination is inevitable for all computable LLMs. Now, let us consider the first main point that the paper provides to support its argument that hallucination in LLMs is inevitable. This first main point is that computably enumerable LLMs will hallucinate. So Theorem 1 directly pertains to this point. Theorem 1 says that for any computably enumerable set of LLMs, there exists a computable ground truth function f such that every state of every one of these LLMs hallucinates on at least one input. In this case, computably enumerable set simply means that it is possible to list out every LLM in this class one by one. The proof for this theorem uses the diagonalization argument and can be visualized in the table seen on screen here. Each row in this table is a particular state of an LLM, and each column is an input string. Each entry corresponding to a state of an LLM and an input string is corresponding to the output of that state of the LLM on that input string. Then, the authors of this paper define f of s sub I to be simply something different from the diagonal entry on row I, column I. Formally, f of s sub I is equal to delta of h hat sub I of s sub I, where delta is a simple computable function that simply flips the answer. In other words, for each input string s sub I, we define the ground truth answer f of s sub I by taking whatever model h sub I or h hat sub I would output on s sub I, and then applying a small flip to function delta, or a simple flip function delta, to make it different. By construction, no matter which LLM or which training state you pick, there's always at least one input where it disagrees with f. So within any realistic family of LLMs, hallucinations cannot be driven to zero. They're baked in by this diagonal construction. Now, let us move on to the second main point that this paper provides. On the last slide, we had Theorem 1, which said that in any reasonable family of LLMs, each model is wrong on at least one input. Theorem 2, shown here in this main point of LLMs will hallucinate on infinitely many questions, Theorem 2 says that for any computably enumerable set of LLMs, the same conditions as the last theorem, we can build the computable ground truth function f such that every state of every LLM hallucinates on infinitely many inputs, not just on a single edge case. The table below is of similar construction as the previous one, where each row is an LLM or state of an LLM, and each column is a test string or input string, s sub I, and the entries on the corresponding row I and column J is what that model would output on the string of s sub I. The output is h sub I or h hat sub I of s of sub j. The blue cells are the ones which we use to define the true answers in the bottom row. For example, our ground truth function f of s sub 0 is equal to delta of the h hat sub 0 of s sub 0. We flip model 0's answer on s sub 0, so model 0 is guaranteed to be wrong there. Further, for f of s sub 1, we do the same thing, but we do it for both models 0 and 1 on s sub 1 and choose an answer different from both. We do this so on and so forth until each column s sub k uses all models with index of j less than or equal to k, and every model's answers appear in infinitely many of these sets, so each model is forced to be wrong on infinitely many questions. So the takeaway from this slide is that even with unlimited training, hallucinations can't be shrunk to a finite list of rare corner cases. There will always be infinitely many inputs where any given LLM disagrees with the true or the ground truth function f. So now onto the third and final main point of this paper's argument for why hallucination is inevitable for LLMs. So far we've covered two things. First, that any computable enumerable family of LLMs, every model in that family is wrong on at least one input. And secondly, you can strengthen that so that each model is wrong on infinitely many inputs. This third point is that any computable LLM will hallucinate. Theorem 3 pushes this all the way to any single computable LLM, not just for an enumerable family of LLMs. Take any computable LLM H. As we train it, we get a sequence of models or states, each state representing a different phase in its training process, as we mentioned early in this presentation. Because training is itself an effective procedure, this whole sequence of states is a completely enumerable set of LLMs, each state representing a different LLM. Once we see it that way, we can just reuse the previous two main points, theorems 1 and 2, and say that for any computably enumerable set, there exists a computable ground truth function f that for every element of the set hallucinates and even hallucinates on infinitely many inputs. Applying that to the set of a given LLM and its states, this gives us theorem 3, which says that for all computable LLMs H, there exists a computable ground truth function f such that for each state of H, it hallucinates with respect to f. Furthermore, there exists a ground truth function f prime such that for each state of H, it hallucinates on infinitely many inputs of f prime. As I mentioned before, a combination of the last two theorems applied to a single LLM. The takeaway is strong here. No matter which computable LLM you pick, and no matter how you train it, there will always be some computable task where every version of that model at every training step hallucinates, and in fact does so on infinitely many inputs. So now that we have established all the main points of the paper's argument and provided and explained all the theorems, we are finally equipped to answer the fundamental question which was provided in our context portion of this presentation, which is the fundamental question that says, is there a fixed training procedure such that for any ground truth function f, the procedure eventually reaches some state of H that matches f on every input? In other words, can we in principle train a general purpose LLM that is completely hallucination free within our scope of a formal world? The box at the bottom is an excerpt from the paper itself, and it gives the answer formally. Using theorems 1 to 3, we've shown that hallucination is inevitable for any LLM drawn from a computably enumerable family, and in fact, for a total computable LLM across all of its training states. Since the real-world LLMs are just a particular computable functions, and in this formal world, the answer to this fundamental question is no, hallucinations cannot be eliminated in the real world. And importantly, this conclusion doesn't depend on implementation details either of LLMs. It holds regardless of the model's architecture or specific training pipeline or prompts that we ask, as long as the system fits the basic definitions from our earlier context slides of what an LLM. LLM is simply a function mapping an input string to an output string, then our conclusion holds for those real-world LLMs. So this slide essentially closes off the first portion of our presentation here. Mathematically, there is no universal training recipe that will give you the perfectly reliable general purpose LLM that is hallucination free. So at this point, we have covered the paper's first main contribution, which is proving that hallucination is inevitable for all LLMs. Now we'll move on to the second one, which is considering how to identify hallucination-prone problems. In other words, now that we know that hallucination is inevitable, where should we especially expect to see it? The paper, visualize the table on screen now. The paper answers this by looking at the computational power of different LLM classes. So we divide LLMs by their computational power, and asking what kind of ground truth functions lie beyond that power. These are the problems that are structurally hallucination prone. So important distinction to make here is that the problems we're talking about are not things that are like information retrieval from a knowledge base, like with an LLM, like asking about some pre-trained knowledge. This is about computing problems. So for these cases, on this table we can see the top row is polynomial time LLMs. An important thing to note is that this class of LLMs is a reasonable abstraction of today's models. Tasks like the combinatorial list problem already require exponential time just to enumerate all strings of length n. Likewise, classic NP-complete problems such as the subset sum, Boolean satisfiability, and propositional entailment, which is co-NP-complete, are expected to be harder than any fixed polynomial time model can fully solve, assuming P does not equal NP. Moving on to the next row, even if we imagine a much more powerful exponential time LLM, there are still problems at the Pressburger arithmetic where deciding whether a statement is true can require double exponential time. Those will remain hallucination prone even for these hypothetical stronger models. Finally, if we zoom all the way out to the final row for all computable LLMs, we run into tasks like learning all computable linear orders or solving all computable problems, as well as first-order logic entailment, which is undecidable. The practical takeaway is that many forms of mathematical and logical reasoning and problems equivalent to these are exactly where we should be most skeptical of LLM outputs. Even if the question sounds simple to a human, if it's computationally hard, it's likely to be hallucination prone for the model. Okay, so we have focused on the negatives offered by the paper, meaning that we had discussed how hallucination is inevitable and unavoidable for certain types of problems, but the paper does also offer mitigators that, given the limits of what we know about hallucination, we can realistically implement some measures to reduce it. The first thing we can do is scale up models and data. What this means is that bigger models with more parameters can represent more complex ground truth functions, and more data usually improves approximation. But our theorems say that if the truth function lies outside of the computational class of model, say it really does need exponential time, then there's no amount of scale and parameters alone that will completely remove hallucinations. The second strategy could be to use smarter prompting. What this means is implementing chain of thought, reflections, verification prompts that when you ask one question, the model actually asks itself several other questions and has checks and balances within its process to steer the model toward easier solution paths and reduce errors on specific tasks. However, this doesn't magically encode all of the truth function f. They're still operating inside the same underlying function class. Third, we can add guardrails and fences. Guardrails constrain outputs to respect human values, laws, and safety policies. This is to restrict LLMs from, producing harmful outputs or to allow hallucination to come at the expense of real-world impact. Fences explicitly mark tasks that should never be fully automated by an LLM, no matter how good it is at the problem itself. So we're trying to eliminate the opportunity for a hallucination to cause a real-world impact or disaster or catastrophe. Finally, we can move toward knowledge-enhanced LLMs. What this means is that we can allow LLMs to interact with systems that can call external tools, databases, or search engines. These start to go beyond a single static function H and are one of the most promising ways to control hallucination in practice. The way you can think about this is, say you ask an LLM a question about some proprietary knowledge that isn't publicly available. Of course, if you ask about someone's birthday that you know, of course the LLM may not have the information for that. However, you can use external tools and it's what's called retrieval augmented generation, where you can have supplementary knowledge bases for your LLM to source that information from. Other tools could include coding or calculators to do computation for the LLM. All in all, though, even with this knowledge-enhanced LLMs, controlling hallucination is very difficult and can't be guaranteed in practice, especially when questions are original and solutions are not necessarily already available for the LLM to source from. So, to wrap up our discussion on theory and mitigation, we'll now spell out the practical implications of what this means to the real world and LLMs. The first is that if you take an LLM that is trained only on input-output pairs, then deploy it as a general problem solver, the theorems we've seen tell us that it will hallucinate. That's not a bug in training, it's merely a consequence of the model being a single computable function trying to approximate many different ground truth functions. Secondly, a pure LLM on its own should not be trusted for fully automatic, safety-critical decisions. Things like medical diagnoses, legal judgments, or high-stakes control systems. To use LLMs responsibly in those settings, we need extra layers, guardrails, fences that rule out certain tasks, external knowledge bases and tools, and ultimately human oversight. Finally, this motivates work beyond just model scaling. We need research and likely regulation around the safety boundaries of LLM use, where they must stay in the loop as assistants, what kind of external checks are required, and how to design systems that remain robust even when the underlying model inevitably hallucinates. So this marks the end of the presentation regarding to the original content and findings of the paper on why hallucinations are inevitable. Now I will be providing a personal evaluation on the paper, including an acknowledgement of the self-proclaimed limitations by the authors on their findings, the strengths of the paper, the weaknesses, and finally, potential areas for future work. So before we discuss some strengths and weaknesses of the paper, we must first acknowledge the self-proclaimed limitations offered and admitted to by the authors. First, the authors point out that their theory does not explain hallucinations on problems that are within LLM's computational capabilities. Their impossibility results are about tasks that are too hard for a given model class, but in practice, we also do see hallucinations on relatively easy questions. They explicitly say that the causes of hallucination are multifaceted, and that this formal angle is only one piece of a larger story. Second, the whole framework assumes a deterministic ground truth function f. For every input, there is one correct output. This is a clean setup for proofs, but it doesn't capture a more probabilistic setting, like questions with inherently uncertain answers, and domains where what we really care about is probabilities rather than a single correct answer, considering what is the likely correct answer here, but instead we're determining what is the correct answer, assuming that there one exists. This paper gives a little insight into those probabilistic perspectives. Okay, so now let's cover the strengths of this paper. First, the paper gives a very clean formalization of hallucination. Instead of arguing about debatable real-world semantics on correctness, this paper defines a formal world of computable strings, treat a trained LLM as a total computable function, and define hallucination as simple disagreement with a computable ground truth function. Secondly, on top of that formal framework, this paper proves strong impossibility results. Using diagonalization, they show that hallucination is inevitable for any computably enumerable class of LLMs, and ultimately for any computable LLM, across all of its training states. These are very general statements. They don't depend on architecture, optimizer, or data set. Third, this paper does a nice job connecting the theory back to practice. The authors map real models to polynomial time LLMs, and then use complexity theory to flag hallucination-prone tasks like NP-complete problems or Presburger arithmetic in Table 3, shown in the slide of problematic hallucination-prone problems. This gives practitioners an intuition for where models most likely fail. Finally, they go back to pure theory and talk seriously about mitigation and safety, how scaling, prompting, guardrails, and knowledge tools fit into this picture, and why we still need human oversight and regulation in working with generative AI. So it's not just a negative result to determine that hallucination is inevitable. It frames how we should think about safe deployment. And I think these are all very strong components to this paper. So this paper is overall very strong with many promising qualities, but there are also some weaknesses and drawbacks as well. First, the notion of a ground truth being deliberately deterministic is imperfect, because as each input string has exactly one correct output string, this is not entirely applicable to the real world. This is a perfect scenario for diagonalization, but it ignores probabilistic settings where we care about likelihoods and distribution over answers. This is much more common in the real world, where not only hypothetically that answer isn't like there isn't always a mapped one-to-one correct answer for something. There's also variability based on outdated information, based on contradicting knowledge, that makes answers not entirely black and white and binary as true or wrong, which, depending on how you classify hallucination in the real world, can make it very murky to diagnose and resolve. This is something that kind of is cherry-picked around in this paper. Secondly, all the theorems are worst-cased, meaning that the constructed ground truth functions are effectively adversarial to a given LLM class. This tells us that hallucinations can't be eliminated in principle, which it accomplishes the task and the aim, but it doesn't really say much about how often they occur in realistic tasks or benchmarks. This is more of the hypothetical concept of what a hallucination is for an LLM, but these worst case examples don't really give us much insight into practical understanding of how hallucinations occur with the models that we use. And good segue into third point, which is that the authors themselves do acknowledge this, but this is a very large component, and that is that this paper does not explain or acknowledge hallucinations on what we would call like an easy problems that lie well within a model's computational class, and we expect it to perform well. However, in some instances, as we know, in the real world using these models, they make errors on very simple problems. And this theory and this paper does not particularly address those cases. So, given both the strengths and weaknesses that we have covered, there are some clear directions for potential future work in this same area of hallucination with LLMs. The first potential future work would be to move beyond deterministic ground truth, extending this formal world to probabilistic labels and predictions beyond just a binary true or like false or correct or incorrect, could connect the results of this paper to statistical bounds on hallucination rates. A second direction to go in could be from just the simple hallucination is inevitable to quantitatively like describing the rate of how much it occurs. Instead of just proving theoretically that some errors must exist by the principles of how models are trained, it'd be interesting to explore if we could bound how frequently they appear for particular task families and explore how those rates are either scaled or impacted by model size and volume of data. Third, it could be valuable as well to formally model real LLM systems instead of abstracting it to just a single function h. This means that they could give the researchers the ability and means to implement guardrails, retrieval augmented generation, external tools, and human oversight as part of the function of the computational model, and then asking what kinds of impossibility or possibility results could survive in that more fruitful setting would be, I think, a very valuable and much more relevant to the real world and our day-to-day usage of LLMs. Now, to conclude, I will pull together some of the main ideas from this presentation regarding the paper on hallucination is inevitable. First, at a formal level, this paper treats a trained LLM as a computable function and defines hallucination as disagreement with a computable ground truth function. Under that model, this paper shows that no computable LLM and no fixed training procedure can be perfectly correct on every input. Hallucination is not just an artifact of today's LLMs, it's an inherent limitation of using a single function as a general problem solver. Secondly, by connecting the theory and complexity classes, this paper identifies hallucination-prone tasks. Problems that are true solutions are computationally harder than what a given LLM class can handle. That explains why certain forms of math and logic reasoning are especially fragile in practice. Thirdly, this paper doesn't say that this is something that is inherently just be a consequence and is a limitation and ceiling on LLMs. The paper argues that mitigation is very possible and present between scaling models and data, using careful prompting, adding guardrails and fences, and building knowledge-enhanced tools. Systems with human oversight can push hallucinations to be rarer, more predictable, and less harmful, even if they never disappear. Overall, the contribution of this paper is a reframing of the question, when will hallucinations go away, to instead asking, given that hallucinations are inevitable, how do we design systems to make LLMs safe and useful anyway?